Welcome back, students. In this lecture, we will discuss the topics simple harmonic oscillation and energy of oscillation, or energy in simple harmonic motion. Okay. So, simple harmonic motion, any oscillation that can be expressed with the sinusoidal function is called as a harmonic oscillation. Okay. So, when the amplitude of this sinusoidal function is constant, it can be called as a simple harmonic oscillation. Okay. And if this oscillation is representing the position of an object, then we can call it as a simple harmonic motion as well. Okay, so you can see here with the passage of time, we are plotting the amplitude of a body, or we are plotting the position of a body. Okay, in that case, here also you can see that the amplitude is constant, so this is nothing but a simple harmonic oscillation and a simple harmonic motion. Okay, let's say that the expression for time is a sinusoidal function, so it could be cos or a sine, and r will be the maximum amplitude. In this case it is 1. Okay, and omega t is the value which gives its phase. Okay, and plus phi is the phase angle or phase constant. Okay, omega into t means it is a theta. Okay. So x of t is r cos omega t plus phi. This we have already seen in the previous class. So velocity dx by dt is minus omega into r sin omega t. Okay, and acceleration, which is d square x by dt square, the second derivative of position, is minus omega into r cos omega t. Here again, r cos omega t is there present in the equation of d square x by dt square. Okay, so we can write it d square by d square x by dt square is equal to omega square into x of t is equal to 0, because r into cos omega t, which you see here, is always present, also present here. So it is d square x by dt square equal to minus omega square into x of t. So taking negative into positive side, we have this differential equation for representing a simple harmonic oscillation. Okay. Now let's see what happens in a spring mass system which undergoes simple harmonic system, harmonic motion. Okay, so you can see that here there is a spring and it is connected with a mass at its end. It is placed over a frictionless surface. Okay, the initial position was this dotted line. Okay, from there an initial displacement of x was given. Okay, obviously what happens, the spring will exert a restoring force on the mass, which is fs. Okay, this restoring force fs is nothing but k into x, where k is the spring constant and x is the displacement. So this is nothing but our Hooke's law. Okay, also whenever this body is moving, when it's stretched, it moves backward and it oscillates about its main position. So this motion is associated with a instant displacement, instant velocity, and also an instant acceleration. So whenever body is moving, of mass m is moving in the velocity, is moving with an acceleration, there will be an inertial force also experienced by the body. So there is also a force of inertia, which is Fy, is nothing but m into mass into acceleration. Okay, so acceleration is nothing but second derivative of position, so m into d square x by dt square. So we have seen that acceleration is nothing but omega square into x, but with a minus sign. So we have Fy is equal to minus omega square into m into x, and restoring force Fs is equal to k into x. Okay, so in order to maintain the dynamic equilibrium, the total force on the system should be equal to 0. So F should be equal to 0. So Fy plus Fs should be equal to 0. So we have minus m omega square into x plus kx equal to 0. From here we can obtain the expression for omega. Okay, so omega is equal to root k by m. So this particular thing, omega is equal to root k by m, this omega is called as the natural frequency of the system. It can be noted that it is independent of the displacement we have given to it, but it's dependent only on the mass and stiffness of the system. So, okay, so this omega is called as it is nothing but an angular velocity or an angular frequency. So it can be converted into normal frequency as omega is equal to 2 pi into f. So the frequency of the system is 1 by 2 pi into root k by m. Okay, once you get that frequency, you can also find out the time period, which is nothing but 1 by f. Okay, we get time period is equal to 2 pi by square root of m by k. Okay, now let's see the energies in simple harmonic motion. So when we talk about energy, there are two things which comes to our mind, which is kinetic energy and potential energy, right? So the kinetic energy is energy possessed by a body by virtue of its velocity, and potential energy is the energy possessed by a body by virtue of its position, right? So we can simply write kinetic energy is nothing but half into mv square. Okay, so we have the velocity in a system is nothing but dx by dt, which is nothing but x0 into sine omega t plus phi. Okay, so substitute that expression, we have an expression for kinetic energy. Also m omega square is nothing but k, so we substitute m omega square as k, so we have this expression for kinetic energy. Okay, so it has to be noted that at time equal t equal to 0, the position is motion is at one of the extremes. Okay, so at extremes the velocity is 0, which means that kinetic energy is going to be 0. So if you try to plot the graph of kinetic energy with respect to time, you can see that at time t equal to 0, when the position of the body is at one of the extreme, you can note that the kinetic energy is 0. Okay, and it increases up to a maximum where the velocity is maximum. Okay, so this position is nothing but the mean position. Okay, again it goes back to the other maximum. Okay, so during this motion the velocity reduces from maximum to s0, so at an other extreme also the kinetic energy is also going to be 0, and this trend keeps on going. Okay, again ut, the potential energy is nothing but the energy stored in the spring. Okay, so you can write it as half into kx square. Okay, where x is nothing but x0 into cos omega t plus phi, which is the definition of x of t for as per the SHM, right? So we have u of t is equal to half into kx x0 square cos square omega t plus phi. Okay, so this is the expression for potential energy. If we try to plot this particular thing at extremes, the potential energy is always going to be maximum, because at extremes the x is maximum, so the potential is also going to be maximum. At the mean the x is 0. Okay, so the potential energy is going to be 0. Again at the other extreme the potential energy is going to be maximum, and this keeps on going. Okay, it is interesting to note that if you try to add up ut and kt together, so if you add this expression and this expression, in both half k x0 square is constant, and inside the bracket you get sine square omega t plus phi n plus cos square omega t plus phi, which is nothing but 1. So at any instant, if you add up potential energy and kinetic energy together, which is nothing but your total energy, okay, the value is always going to be half into k into x0 square, where x0 is the initial displacement or the maximum amplitude, right? So that is one interesting thing to note. The total energy is always a constant. Okay, so at mean position you can see that the kinetic energy is maximum, and at the extreme position the potential energy is going to be maximums. Okay, so the total energy in a system can be written as mv square, half mv square plus half kx square. Okay, at an instant, and it can also be written as at equilibrium position x is equal to 0, which means that the total energy is fully kinetic energy, so it can be written as half into m into v0 square, where v0 is the speed at the mean position or velocity at the mean position. Or also at extremes the velocity is going to be 0 and x is equal to amplitude. Okay, which means that the total energy is all the potential energy. Okay, in that case I can write it as E is equal to half into k a square by half into k a square. Okay, so total energy is either half into k into a square or half into m into v0 square, where v0 is the velocity corresponding to the mean position, or it's the maximum velocity. Okay, so with relation to this, we have a question here. A 200-gram mass is attached to a spring and it executes simple harmonic motion with a speed 0.25 seconds. So time period t is given. Okay, mass is given. Okay, from this mass and time, you can find out what is called as omega, and from omega and mass is given, you can also find out the spring constant k. Also, you have to find out the amplitude of the motion with the given total energy is given. Okay, so let's see how to do this. So with the given time period and the given mass, we'll use the equation for time period and find out what is called as k, or the spring constant or the force constant. So we get k. So it is important to note that whenever you are using this particular equation, okay, time period will be given seconds, k should be substituted in Newton per meter, and mass should be substituted in kilogram. Okay, so we get k is equal to 126.3 Newton per meter. Okay, also the total energy is given as 2 meter. Okay, we have the expression for total energy. It is either half into k into amplitude square, or it is half into m into v0 square. So here we are required to find out the amplitude. So we can use total energy is equal to half into k into amplitude square. Okay, so amplitude is unknown, u is given, total energy is given as 2 joules, and k is also just what we found out here. Okay, from this, substituting these values, we get a is equal to 0.18 meters. Okay, this simple topic, we'll continue with more topics. Thank you.